Awesome. First of all, thank you for having me at MLconf, and it was a pleasure before and this year in this virtual setting. Thanks for organizing everything perfectly, and hopefully it will be a much better experience for everyone. So today's topic I will talk about is heart-to-heart and eye-to-eye with deepfakes. And what I mean by that is actually heart-to-heart, which you can see the pulse information here, and eye-to-eye, which is the eyes of different deepfakes and the real images here. So we will see about how we can use those heart and other biological signals to detect deepfakes. Before that, a little bit about me. You can share, tweet, do everything, and reach out to me from these links. I particularly like this photo of mine because it was actually me at MLconf 2018, and it was a pleasure to share what I was doing at that time, and it's now a pleasure to what I'm share to be a part of MLconf 2020. And when I say Intel, it is Intel Studios. If anyone doesn't know, this is the huge dome down in LA, which is 10,000 square feet and doing volumetric capture. That is the world's largest volumetric capture space. Let's start. So, what is this bombardment of all the news headings, right? This is what you will learn today. So all these news pieces are from our work and from using pulse and heart rate to find deepfakes. And as seen in all of these news outlets, let's start the presentation. So why are deepfakes a problem right now, right? There has been many advances in GANs, in AI approaches for compute power, for open sourcing resources, for many developments to have them more trained more easily and sharing more easily. And for example, variation autoencoders is one of the first ones. Then all the advancements like LSGAN, PGGAN, CycleGAN, now StarGAN, StyleGAN, V2, etc. So these are all technical advancements in GANs and in AI that enabled deepfakes. And what are deepfakes? As you probably already know, or as you can see from those images, these are portrait videos which are synthetic and which are mostly impersonating other people. It may be deepfakes of people that don't exist at all, or it can be people that we know. I think the most known one is the Obama that is giving some information about deepfakes, etc. So there is also the dystopian scenarios on deepfakes. There's they are used for political misinformation. Most of the use cases for deepfakes are for porn and celebrity porn. There are fake court evidences, impersonation, forgery, and it is foreseen that this will cause a social erosion of trust. So this pushes us more for authentication and detection approaches for battling with deepfakes. So, of course, for detection of deepfakes, there are several approaches that are already published. Some of them look at the color changes. Some of them look at the head pose and consistent head pose, like if the deepfake is all looking at one place. And some of them are looking at other signals such as blinks. We actually divide them into pure ML-based approaches or face priors. So these two would be face priors, and this would be pure ML-based approach. Our intuition for fake catcher is actually most detection approaches that I just talked about look at the fakeness and how fakeness have its faults. Our approach is, on the other hand, looking for a unique authenticity signature in real videos. And there is a signature there. So our own heart rate, our pulse information, has been examined in remote PPG settings for many different applications, for health monitoring, for patients diagnosis, etc. So these remote heart rate signals can be used for deepfakes too. What are those signals? So blood flow creates subtle changes. So in your veins, there may be some changes, the color changes and motion changes that is invisible to the eye, but visible computationally. So photoplethysmography, PPG, is actually measuring blood pressure via skin color change. That's what we are using. And no generative model can create deepfakes with consistent PPG signals yet. For fake catcher, we first started with the question, given n pairs of fake and real videos, can we find an implicit indicator of biological signals? That being said, this is just a pairwise setting. So there is one fake video, one original video, and they are the counterparts. Can we say with high confidence which one is fake, which one is real? And as you see the GPPG and Chrome PPG signals here from the original and the synthetic image, they actually, the heart rates and the signals vary dramatically. So based on our analysis of those signals, we can check the paper for more details, but based on our analysis, we can actually find an implicit function, not even a deep neural network. We can find an implicit function using pairwise cross-spectral densities, and that gives us 99.39% accuracy for the pairwise separation problem. And as you can see, the cutoffs for the cross-spectral densities are actually very nicely shown, nice behavior for fakes and reals, which is very intuitive, right? Like for fakes, the heart rate from your left cheek is not matching the heart rate from your right cheek, and that is something we can formulate an implicit function. That brings me to the generalization. So now we know the answer to the pairwise problem, pairwise separation problem. Can we actually generalize it to any video in the wild? And for that, since we know some of the feature space, we first go with the traditional approach. We tried an SVM on that feature space of like autocorrelation, some of the coefficients, some of the other transformations, and we reached a 75% accuracy by using a kernel-based SVM for classifying any video in the wild. However, 75% is not that good, right? Like I can say that this is maybe fake, but so we looked for more clues. Like, is this space more complex than we assumed? We did some PCA for the components. We did some linear discriminant analysis and source separation approaches, and we found out that yes, the space is more complex, and we can lift it to a higher dimensional space so that we can classify them more easily. For that, we use a simple CNN. This CNN just has 3 layers, just to add, just to reach to that level of complexity, so that we can classify. And this gives us 96% accuracy if we just use a 3-layer CNN for that. We also did other analysis. We looked at which parts of the face we should take, and we, as you see here, we did all this analysis. We compared our approach with other approaches like inception, exception, more complex architectures, but without biological signals. And as you can see, those we are better than the most complex baseline by almost 9%, just because we are using biological signals. We also did look at some synthetic blur, some synthetic image processing approaches to find out why, to see our robustness and how much such operations we can accommodate. We also looked for multiple faces, or a fake video with low face detection confidence, or a real video with low detection confidence. And since we aggregate all of those features, we can actually still classify them easily. Our last contribution for fake catcher is the fake catcher is the deepfakes dataset. So in this dataset, we collected many videos from many different resources, from YouTube, Twitter, presentations. Whenever we see a deepfake video, we edit that, and that actually. We try to encompass all the like illumination, occlusion, makeup, pose, different generators as the datasets in one dataset, so that we can actually have a real baseline for deepfakes in the wild. That brings me to another aspect. So instead of saying whether it is real or fake, can we actually do source detection for generated GAN-generated imagery? There are some approaches like GAN fingerprint or like clustering the artifacts, etc. And can we do it for deepfakes? So this is our pipeline for finding the sources for deepfakes. Which model does this deepfake come from? Instead of using biological signals as the authenticity signature, we actually want to see biological signals as the projection of generative sources into biological domain. And as you see here, there is actually a real difference between different fake generators. So this is a real frame. This is the all different deepfake generators. And in the PPG domain, you can actually see them a little bit more emphasized way. So the signatures change very drastically. So how can we go to that route? I will give a very brief intro of the approach. So we first extract the frames from the video. Then we divide them into omega length windows. Then we find the faces in each sequence. Then we find the regions of interest in each sequence and align them using Delaunay triangulation and nonlinear affine transformation. So here you can see that it is most likely a rectangle, the region of interest. Then we divide this signal to equal squares per frame and extract PPG values per each square. Then the PPG values are converted to a PPG map where we have delta values per frame and then omega sequences per map. Then we also concatenate the power spectra of those signals and scale it back to omega. So this PPG cell is what we are classifying on. For sequence classification, it's a multi-class classification of PPG cells with this simple CNN architecture, equally probable classes for generators. For the CNN backbone, we used VGG19, and we also had we tried with other backbones. VGG19 is the best between like having the model capacity enough and not overfitting. There's also the video classification after window classification. So we need to aggregate those per window solutions to per video prediction. When we tried majority voting, occlusions were sometimes dominating. When we tried thresholding, it is too ad hoc. At the end, we used log of odds to actually classify them correctly based on their confidences. This is our confusion matrix for source detection. You can see that like we have overall 93.39% accuracy for source detection. The worst one you can see is neural textures. It's 81% accuracy, and we are still improving these results. We can also extend to new models. So without the dependency on the model architecture, without the dependency on the original videos of the original videos that those models use, we can actually extend very easily. So for that, we took 1,000 random fakes from celebDF dataset, which the model didn't see before, and retrained it not based on 5 classes, but based on 6 classes. That further improved our fake detection accuracy to 96.89. And for celebDF, we still had 92% accuracy, even though the model never saw the reals of celebDF. So this is a nice improvement towards like generalization to any deepfake in the wild. We did ablation studies. You can check the paper for that. We checked for window lengths and which windows is long enough to capture heartbeats and short enough to not bring out the noise. We also looked for unseen generators. So this is just on the inference time. We created a new data set from 48 real and fake videos from these 5-6 data sets. And we looked how, in the inference time, how our model behaved. So we saw that real becomes the chaotic state without an exact signature because there is no generative noise in real. However, even though there's compression artifacts, etc., we can still see that the face forensics fakes, which come from face-to-face generative model, are correctly classified. Another important part here is the deepfakes dataset, where you can see that this comes from many different resources, and some of them comes from face-to-face, some of them comes from neural textures, etc. So even though in that mixed state, we can actually find which models they come from. That brings me to the eye-to-eye part of my presentation. So can we actually utilize more priors, more biological priors to detect deepfakes? This is a very simple binocular vision image that when you look to something at 3D, your eyes actually converge on that on one point. And if it is distance, they still on the same plane. And if it is near, like the screen or like some prompter, they are actually in the close plane. So if these eye vectors are on the same plane, you can actually say that it is a real person. And we looked at several data sets to find whether those eyes are fake or not. So here you can see that these are the real eyes, and these are all column-wise different generators creating different fake eyes. And you can see some of the artifacts are visible, some of the artifacts are quite not visible. But if you carry that to the geometric domain for gaze points, you can actually see that fake gazes exhibit noise like this. It's not like you see, it's not perfect. They miss some saccades, so there are different eye classes. So they can mix some saccades, or some fixations can be longer because it's not updated correctly. And they actually have quite irregular distribution, as you can see here. And there is actually the regularity of the real one here is actually lost. By the way, sorry, I don't have the labels here. This is the real 3D gaze points, and these are the gaze points of several different deepfake generators. So we can actually classify based on these gaze features. And for now, we have 71% accuracy with very simple baselines. But we are working on that to actually explore this gaze space in a more theoretical manner, so that we use the underlying geometry and underlying biological information for improving the deepfake detection. So my key takeaways, deepfakes have hearts with unique heartbeats. Of course, these heartbeats are not real heartbeats, but those are generative noise that can be used as a signature. We propose the first method to detect the deepfake videos in the wild. We believe that generative residuals have stronger discriminative features when projected onto the biological signal domain, as I've shown in many of the examples. We also think that this is an adaptive method to new generative models with similar accuracy. And it is very important for continuous integration and deployment, because, you know, every day there's a new deepfake generator. If we can classify and divide them into different classes, then whenever there's a new generator, we can actually classify it, and we can do maybe different approaches for detect it, or we can analyze the samples of that new generator separately, so that we can be better armed. So thank you. This is my contact information. I will just check the time. And if you have any questions, I can happily answer them.
Hello, Ilke. Great presentation. This is Pamela. We do have a question from the audience, from Vinod. The question is, do you consider changes to biological signals, heartbeats, pupils, related to the emotional content of the video, especially when the speaker in the video talks about emotional topics?
Oh, that's a very good question. I know that some of my colleagues actually looked at not the emotional state, but the action units on the face to detect whether they are consistent for finding deepfakes or not. But I would say, obviously, emotional state can be one of the priors that we depend on, because that also has a consistency in human space, right? We cannot be like angry in one frame and happy in the other frame. I mean, of course, there are some facial actors that can do that, but in regular videos where that is not the focus, that can actually be a nice indicator of consistency among different frames. And of course, both the gaze information and heart rate information is depending on the emotional content, emotional state of the actor. However, even in that case, even if those are changing, they are changing consistently. Just because you are more emotional, your heart rate on your, I'm giving the same example, sorry, but the heart rate on your left cheek will be different from the heart rate from your right cheek. So even if that information is changing continuously for one actor, that is still consistent in spatial and temporal domain, so we can still use them for defect detection.
Thank you. And we have a double set of questions from David. He asks, 1, do you expect these biological signals to be faked in the near future? And 2, do you want to answer that one first? Or you want to take them both? Let's take the first one by a time.
I was prepared for that.
Okay, go ahead, and I'll come back with the second part of his question.
Okay, the answer is no, at least in the short term, no, because there are 3 reasons for that. One, by the way, like I prepared a slide for that just because like we keep getting this question so much, so that I thought like it is good to be prepared for that. So one, to incorporate PPG signals into the loss function, that can be different. The PPG extraction should be differentiable, and since it's not different, like the actual way that we extract is not differentiable. It's like a complex way of like thresholding and finding the PPG from different signals in temporal and spatial, etc. So it's not easy to just say that, okay, I will just like plug it, the formulation, and like back probe and etc. That is why it can't be done in the near term. Second, mimicking both spatial and temporal consistency of those many signals from the face is actually hard, because even if you have some approximation for the PPG, you need to keep that consistent. It's not that we are saying create a deepfake with 75 heartbeats for all of the videos, all of the duration. That is not even like, that is robotic, and we want that to be a normal heart rate, sometimes going up, sometimes going down, but spatially and temporally consistent. And mimicking that prior is also hard. And lastly, even if you don't use the exact PPG formulation to have an approximation to a PPG signal by learned methods, you actually need large ground truth PPG datasets to learn that approximation. And the actual PPG signals that you extract from videos cannot be like RPPG may not be your best ground truth, because they are very fluctuate. They can be noisy. They are not like the real PPG signals. And there is no, almost like there are some, but there is no big PPG data set that can be easily used right now. I mean, there is one in my collaborators' lab, but there's not much so that you can actually learn and approximate to PPG so that you can incorporate it in your loss function. So in short term, no. In long term, maybe.
Excellent. Here is the second question from David. Can we use these techniques to monitor online content?
Obviously. So what we are planning to do is actually, you see we have the dataset link here. We actually want to put out a website or an interface so that everyone can upload a video that they suspect that can be a deepfake, and they can actually see whether it is a fake video or not. And I think such tools should be open to general public, so not just like for some media representatives, or not just for some news outlets, etc. But everyone can do checks of videos, whether they are deepfake or not. And like there are some fact-checking websites that people can go and check whether it's fake news or not. We want the deepfake detector to be something like that. And I know that there are some companies out there and some nonprofits out there working in that domain. And I hope those collaborative efforts will actually give us some more leverage over the deepfake generators, so that we can actually have that ensemble of networks, not just fake catcher, not just like Blinks, not just Mesonet, but all of them together, giving some intuition about a deepfake video, so that we can better arm ourselves and we can be better informed. And the social erosion of trust scenario never happens, because people know what to trust and people know what to follow, etc. So I think it's very important to publicize those, at least interfaces, maybe not the methods, but the interfaces, so that everyone can do those detections.
Great. We have a question here from Carlos. Do you think there are other biological signals that could also be used to help identify deep fakes? For example, breathing or others?
Lovely question. Yeah, so what I was trying to go here from heart race to eyes, and it's also in my title, right? Like heart to heart, eye to eye. There can be more biological priors, like breathing can be one of them, or for example, if you can see the neck, maybe the vibration of my sound in my neck, for example, another biological prior, or maybe even like the behavioral clues, right? Because those behavioral clues can be much more personalized and can be harder to detect. Like, I don't know, sometimes maybe when I'm talking, maybe I'm like looking so much around, or maybe I'm smiling in a consistent way that like maybe every 100 frame I have that behavioral aspect of smiling, or etc. So all of these, both like biological and behavioral traits, can be used. And what I can be used to detect deepfakes, because they are not easily replicable. And for example, like there are some other detection approaches that are looking at in an individual person level, because it is easier to generalize those behavioral aspects per person than to generalize it to all public, right? So there is a paper that is looking only the world leaders like Obama, Trump, etc. And they are customizing those deepfake detection models per that person, so that that person's both behavioral and biological and whatever implicit information is encapsulated, is captured in that deepfake detector, and the deepfakes cannot go into that individual level of replicating the person. So I hope this is a good answer.
Thank you, Ilke. One more question here. We have Vinod, who asks, does the effectiveness of PPG identification vary significantly based on the skin tone and or other racial characteristics?
Very good question. We want to be a little bit further away from that discussion and assume that the PPG models, the PPG formulations that has been used for several years in different domains have already tackled that question. So we are not reinventing PPG. We are not reinventing biological signals. We just want to use them to do this detection. That being said, we can never be through scientists or through like fair people, if we say that, oh yeah, that is someone else's, like PPG being fair to everyone is like someone else's problem, it's not my problem, I will just use it as it is. So we cannot do that. We did we haven't add that to our paper, but we did internally look at the edge cases, and if we can detect some of them easily, some of them hardly, the confidence changes, etc. And because the Chrome PPG that we use is not actually looking at the real color, but it is a combination of the reflectance model and the color values. It is so we could have used different PPG signals. There's GPPG, Chrome PPG, the PBV, I guess, etc. So all of these have different aspects. And Chrome PPG, we found out that it works the best for different skin tones, more generalizable, more robust to color changes, illumination changes, etc. We want to do maybe this is like future work information, but we want to do a more elaborate analysis of all those deepfake approaches for different skin colors, different ages, different makeups, different maybe even like behavioral traits, etc., and find out if we if there are any edge cases, if that we haven't accommodate for.
Great. Okay, folks, any last questions here for Ilke? Give you a minute to enter your questions. Great job, Ilke. Very fascinating information. I'm amazed.
Thank you. I think in the benefit of the timing, I went a little bit too fast in my presentation, but I hope it was understandable, and I hope I was able to give all the information that I wanted to deliver.